Hello students, welcome to KlassPM. We are discussing rotational spectroscopy. In the previous class we learned the energies of the rotational spectroscopy, and today's class we are going to learn what is the selection rule for this rotational spectroscopy. So when it comes to the selection rule of rotational spectroscopy, the transition occurs between two successive energy levels only, which means, so these are my different energy levels. So epsilon 0, epsilon 1, epsilon 2, epsilon 3, epsilon 4 with respect to J values 0, 1, 2, 3, 4. Okay, now here the transition always from one energy state to its immediate successive higher energy level, E0 to E1, but E0 to E2 is not possible. If it want to go to E2, it will go from E1 to E2, then E2 to E3, E3 to E4. So the transition always between two successive energy levels. In another way also you can say that plus or minus one transition is allowed transition, but plus or minus 2, plus or minus 3, plus or minus 4 and all these are forbidden transition. So this is an important thing, that what is the selection rule for the rotational spectroscopy? The transition always occurs between two successive energy levels. So it is always from E0 to E1, but E0 to 2 is not possible. At the same way, E1 to E3 and E1 to E4, it's not possible. Only two successive energy levels only possible. That is, plus or minus 1 is the allowed transition for the rotational spectroscopy, and plus or minus 2, plus or minus 3, plus or minus 4 are the forbidden transitions for the rotational spectroscopy. And here one more thing we need to understand, that is, here how much electromagnetic radiation. See, here one molecule is there, you are sending electromagnetic radiation to this, that is a microwave radiation only we are talking about. So microwave radiation you are sending through this molecule, so that what happens, it is absorbed that energy and it is went to the first energy state. From there it is went to the second energy state, third energy state by absorbing much energy. See, this absorption energy, that is intensity of absorption of microwave radiation, is depends on what? It depends on the number of molecules present at that energy level. Okay, if more number of molecules are present, more absorption takes place, so more reduction in the intensity of electromagnetic radiation on incidenting molecule. So more, it is depending on what? The number of molecules present at that energy level, how many molecules are absorbing energy, so that much energy intensity is reduced and it will go to next energy level by absorbing that energy. Here we need to remember that. So the amount of energy absorbed depends on the number of molecules present at that energy level and how that absorption. And one more thing here you need to remember, if equal molecules are present at different energy, for example we have 1000 molecules. These 1000 molecules are equally distributed, that at first energy level 100 molecules, second energy level another 100 molecules, and third energy level another 100, like that till J9. All 1000 molecules are equally distributed at different energy levels. In that case the intensity is also same, because the same number of molecules are present at different energy levels, so that the intensity from E0 to E1 is same, the E1 to E2 is same, E2 to E3, E3 to E4, E4 to E5, E5 to E6 and so on. All these intensities in the transition from the lower energy level to higher energy level are same, because same number of molecules are present at all the energy levels from E0 to E10. But in reality this is not possible, because same number of molecules do not present at the same energy levels, and that to find the number of molecules present at different energy levels, we have Boltzmann law of distribution is that is Nj by N0 is equal e to the power of minus Ej by Kt. This is the Boltzmann law of distribution, we call it as. Here Nj is the number of molecules, the population of molecules at J energy level, N0 is the population of molecules at ground level, and this is the energy of J level, and the K is the Boltzmann constant. Its value K is equal 1.38 into 10 to the power of minus 23. It's called Boltzmann constant. and T is the temperature in Kelvin. So by using this particular formula equation, we can derive the number of molecules present at different energy levels while comparing with the molecules at the ground level. Okay. So here what is describing? Nj is the population of molecules at J energy level, N0 is the population of molecules at the ground level, and E is the energy of J level, and K is the Boltzmann constant, its value 1.38 into 10 to the power of minus 23, and T is the temperature in Kelvin. So those are the values are given. Let's find out, let's take one example and try to find out how do we find the population at different energy levels. So this is a formula we have given, that is a Boltzmann law distribution. Now we know the value of Ej, we already found it, okay, we already discussed that. Let's substitute that value there. So e to the power of, its value how much? It is given h square minus h square by 8 pi square I into j plus 1. This is the value we have taken. Now so that how it will change again, and we have taken this entire part as b. So e to the power of minus b into j of j plus 1. So nj by n0 is given by like and divided by kt. This is a formula if you are using in terms of per centimeter. So in joules, e to the power of minus b j plus 1 by kt into hc. This is a formula we can use to get it in joules, and this is in centimeter inverse. These are formulas we can use. Now the ratio of the population depends on what? Let's take it for a given j value. Here j value is given, so j is given and the remaining all are constant, so that nj by n0 is directly proportional to what? E to the power of minus b. Okay, so all these values are constant for a given j value. So nj by n0 is directly proportional to the eb. So for this what I calculated is e to the power of minus 5, e to the power of minus 10. So here you can observe that the population are at the different energy levels as compared with the ground energy level. The population ratio, the relative population ratio of the molecule is directly proportional to the e to the power of minus b. E to the power of minus b in the sense of generally you can take it as like this, j into j plus 1. Okay, this is already constant, b is already constant. So you can say that it is directly depending on what? Minus j value. As j value increases, what happens? See here j value have taken 5. I got the value 0.006737. I increase j value to 10. What I got is 0.0000453. So if j value is increasing, what happens? The total value of e to the power of minus j is decreasing. As j value increasing, what happening? E to the power of minus j value is decreasing. If e to the power of minus j value is decreasing, what happened? Nj by its the relative population ratio of nj and n0 is also decreasing. So as you are going above higher energy levels, they are having less number of molecules. Okay, when we are going to higher energy levels, so different energy levels. So this is j is equal to 0, 1, 2, 3, 4. As we are going above, as j value increases, what happens? The population density is keep on decreasing when comparing to the ground level. That is the conclusion you can make. Another factor which is also influencing. See in this formula, the relative population density of molecule is inversely proportional to what? At the denominator what is there? Temperature is there. Nj, because that is not, it is a variable, it's keep on changing this temperature. K is a constant, Boltzmann constant. J plus 1 values keep on changing. How j plus value? See in our formula, b value is constant, k value is constant. Only variables are temperature and j value. This is already we have seen. If j value increases, what happens? The relative population density is decreasing, which means number of molecules at higher energy level are less, the number of molecules at the lower energy levels. That is the conclusion. Next, how this temperature is influencing? So e to the power of minus 1 by t. Let's substitute these temperatures. Here you can see that I calculated for 300 Kelvin and the 400 Kelvin. temperature I have taken 300 Kelvin, so that I got 0.9966. So last numbers you can see that is 966. If I take the 400 Kelvin, I got 0.9975. So 966, 975. So if temperature increases, what's happening? The number of molecules, the relative population of molecules also increasing. So from this, what you can conclude is, two conclusions we can make from here. See here, what is the formula? Relative density of population Nj and naught is equal to e to the power of minus b into j plus 1 by kt. This is our formula in wave number terms. If it is in joules, you have to keep just h and c here. Now here, k is a constant, b is also constant. So only variables are what? J and t. How j is influencing? Nj by n naught is equal to e to the power of minus j. If j value increases, what's happening? So I calculated per e to the power of minus 5, that I got 0.006937. And also calculated for e to the power of minus 10, I got 0.0000453 I got. See here, as j value increases, what's happening? Total e to the power of minus j value is decreasing, which means nj by n naught value is also decreasing. So at higher energy levels, if we are going, j value increases, so that the population of molecules also decreases. This is one conclusion. If we draw a graph for this, so here I have taken nj by n naught on y-axis, here I have taken j value, that is 0, 1, 2, 3, 4, 5, 6. So that what I got is, I got a graph like this and I got a graph like this. So this is a graph for if j is equal to minus 5 centimeter. This is a graph I got for b is equal to minus 5 per centimeter. And this is a graph I got for b is equal to minus 10 centimeter per inverse. See here, what is the difference between these two graphs? As b value is increasing here, as j value increasing, the drastic reduction in the number of molecules at the higher end level. So sharp reduction. Here the slowly reducing. So this is what. When it comes to the temperature, Nj by N naught is e to the power of minus 1 by T. So T is equal. Let's try to understand with the example. So here I have taken e to the power of minus 1 by 300. So that I got 0.9966 I got. If I take e to the power of minus 1 by 400, I got 0.9975. See here, 6675. As temperature increases, the population, relative population also increases at higher energy levels. We will take one example and we will calculate how it will be found. I hope you understand how the relative population at different energy levels changes based on J value changes and temperature changes. If J increases, population is decreases. That means at higher energy, less population. As temperature increases, but what happens? More molecules will go to the higher energy level. That's why the population at higher energy level will be more. Let's calculate the population, relative population ratio for E0, E1. That is at ground level and at J energy level. That is first level if J is equal to 1. Now we'll try to calculate the relative population ratio for Z is equal to 0 to J is equal to 1 energy levels. So we have the formula Nj by N naught is equal, that is number of molecules at J energy level, number of molecules at ground level. And this is a formula I have taken in terms of joules, that's why I added Hc here. Let's calculate this one, how it is possible. So Nj N naught is equal to e to the power of. So at one energy level, B value how much? We already know that the B value is 2 at one energy level. So you can refer the previous classes. I have given 0 at a ground level, it is 0. At second level it is 2B, and next level it is 6B, 12B, that we already discussed. So here B is equal to how much? 2 into J value how much? 1. 1 into 1 plus 1 into Hc. H value, it's a Planck constant, 6.626 into 10 to the power of minus 34, and the speed of the light, that is 3 into 10 to the power of 10 meter per second. Okay, no need to write the units. Let's calculate. And Boltzmann constant, its value 1.38 into 10 to the power of minus 23 into, let's take the temperature, some 300 Kelvin. At room temperature I'm taking 300 Kelvin. Let's calculate this. So I'm not taking E later. Let's simplify this part, then add E value there. So minus 2 into 1, minus 2 into 1 plus 1, 2 into 6.626 into 3 I'm writing into 10 to the power of minus 34 plus 10. 10 to the power of minus 34 plus 10. I'm also bringing this minus 23 to the numerator, so it will become plus 23 by 1.38 into 300. So this is total e to the power of. Now simplify. 2 to the 4, 4 3 is a 12. E to the power of minus 12 into 6.626 into 10 to the power of how much will be remain? 10 plus 23, 33. 33 minus 34 is minus 1. So minus 1, since it is minus 1, 10 to the power of minus 1, I am writing that one in the denominator so that it will become 3000. So this 10 I am writing in the denominator. 10 to the power of minus 1 I will get. So minus 1 means it comes to the denominator. It will become plus 1. 1.38 into 300 into 10, that it will become 3000. So by using calculator, let's do this calculation, how much we will get. So after calculating, I got this Nj by N naught value 0.9810, which means almost it is equal to 0.98 means it is almost equal to 1. So which means what? In the first energy level, that is ground level energy level, and J is equal to 1 energy level, the number of molecules are almost same. Same thing you are going to calculate for J is equal to 3 as compared with J naught. So in the here we are comparing with always ground level only. So you will come to know that it is always you don't get same here. Here almost same. The number of molecules at J naught and J1 it is same, because we got almost equal to 1. Very less number of molecules are difference is there between ground level and the next energy level. But as you go above, the number of molecules are keep on decreases. That you can, the same way you can calculate, and you can also find that. So in the next class we are going to discuss a few more topics left in the rotational spectroscopy that we will discuss in next class.